So let's think about unsupervised dependency parsing. But before that, please watch my playlist for dependency parsing before going to the next slide. So in your conversational AI, your voice bot, you talk, and then it is an NL query, which is in English, and the tokenizer creates something, but we need part of speech tagger because as I have explained in the playlist of dependency parsing, you need these features, part of speech tagger, in order to do the algorithm for dependency parsing so that it gives the output, the parsing to the build SQL query. So think about it as another algorithm, which is semantic parsing. So this is the structure of my robot. So you can do it for yourself and create your own type of chatbot. This article, in order to explain 2014 article, I need to, because it is dependent and very similar to this idea of bootstrapping feature-rich dependency parsers with entropic priors, written by amazing scholar David Smith. So what is this article is about? And one may need to build a statistical parser for a new language using only very small labeled tree bank. You see those universal tree banks, those English tree banks, those are specified, those are restricted to English language. So we cannot use it for Spanish. So because in Spanish, in Greek, Persian, or even old languages such as Sanskrit in India, because we have very small labeled data, the parsing of those sentences that are written in these languages, and that's a big problem. So we have a scarcity in our resources. So what can we do? This is the approach of Ryan McDonald, and so each directed edge in the dependency tree is described with a high-dimensional feature vector, as I have explained in my playlist on dependency parsing. So you can skip this slide if you know what I mean. And then the parsers of translation, for example, Spanish to English, could be like an alignment, because if P prime is a translation to English, if C prime is translation to English, then you find a pairs. But sometimes you cannot find a pairs. You cannot align them. So I will explain how you can transfer these weights. And what if they are not aligned? Then how can you transfer the weights? So the idea is that we have a sentence in English and we have a sentence in Spanish. You see, 1, 2, 3, 4, 5. We have 5 words for Spanish. 1, 2, 3, 4, 5, 6, 7. But we have 7 words for English. So it probably cannot do a good alignment. And I will explain this function K, which is really important. It's a kind of, and here I will explain why we need this. Labeling distribution is P tilde, but this one is for English because we have the resources, we have good training data, good supervised training data. For each sentence, we have a tree. For another sentence, we have another tree. So we have lots of training data. Let's say pair of S&T for English. But we don't have, there is a scarcity for other languages such as Persian, Greek, Roman, Sanskrit, Spanish. So what we do is we want to use this labeling distribution. So this article is about that. When we call it transferring distribution. And of course we do entropy regularization as well. So as I said, we have resource-rich language such as English here. We have here for Persian, for example, and then we manually annotated tree banks that these parsers rely on are highly expensive to create. We should pay to people to do that, and so. In particular, when we want to build tree banks for resource-poor languages, we need this. And this is a good association with the methods of hierarchical reinforcement learning that I really like, and I just wanted to show you that you can think like this as well. Dependency parsing applications are huge. Synonym generation, relation extraction, machine translation. Let me add question answering. I want to add text summarization, and sense ambiguity, and so lots of things. So what is the goal? We want to build a statistical parsers for resource-poor target languages using existing resources, such as English. And we propose a learning framework for transferring dependency grammars from an English to, for example, Greek. There are absolutely no labeled training data for the target. For example, it means that in your Greek language, assume that we don't have a tree bank for that Greek languages. Or if we have, it's so little that we just ignore it. So why is generic dependency trees treated as a set of edges? X is a sentence. And after training, you see that you can have this, I've explained these weights on my playlist because you can use both graph-based. For example, in graph-based, we learn these parameters. In graph-based, in the third lecture of my playlist for dependency parsing, you will learn this. So now this P is ready because we have learned this. And as usual, this z of x partition function, most of the time machine learning is intractable, but here it's different story. We have a finite set of training data and assume that there is no problem. So edge factored parsing model, we can just multiply them because they are independent probabilities. And for model training, we just need to maximize the likelihood. So the K function is a generalization of our idea of Smith. P tilde is transfer distribution, reflects her uncertainty about true labels. This is what we have learned. So this is okay, but this P tilde, we need to work on that. So we have some source sentence, such as English, some target sentence, such as Greek, and then we have alignment. Hopefully, alignment can do everything, but sometimes it is not aligned. So the K function, this is our target. This is our loss. We want to minimize it, as usual in machine learning. And so K can be divided into two cases, whether xi belongs to the parallel dataset or unlabeled dataset. So how can we define this transfer function that we have already talked? So we assume the target is Spanish or German here in this language. For example, we have 6 words for this sentence in English, but we have only 5. So we can anticipate that there is a misalignment. There is not a good alignment. For example, research area is just one word in Forschungsgebiet in German. So NLP is ein schönes Forschungsgebiet. But in English, we say it differently. And so we can use these translators. So if we can align, just use the weights of the English one, of the source, which is the English. But if it is not, then you use the delexicalized form, which is explained in this paper. So the delexicalized form of the edge. and which is explained in this paper. But what are the reasons that we do this technique? Why do we design the solution like this? First of all, we can project the syntactic information across language boundaries. And second of all, which is really important, McDonald, this great guy from Google, says that in 2011 says that it demonstrates that parsers with only delexicalized features produce considerably high parsing performance. By reducing unaligned edges to their delexicalized form, we can still use those delexicalized features, such as part of speech tags, for those unaligned edges. So if it is not aligned, no problem. We use the delexicalized features, and that's it. So a tree Y has many edges, such as E. And if we multiply all of them, we get P tilde. And this omega tilde, we have just designed it here. So everything is ready. The transfer distribution is ready. So go on and minimize this objective. So for the parallel data and unsupervised data, we do it separately. For parallel data, we do it like this. We need the gradient because we are using gradient descent, so we need the gradient. For unlabeled data, the same thing. We have a different gradient with respect to lambda. And after all, that's it. When you just add them together, then you know how to design these lambda. Lambda is lambda plus the gradient. And then you learn it until it converges. And then you have already learned the parameters of this model.